Alright, so in this video we are going to begin chapter 8, which covers functions of several variables, partial derivatives, double and or multiple integration, and optimization, and obtaining max and mins of functions of several variables. So we will begin this chapter by looking at what a function of two variables or two or more variables is, or several variables, just for the sake of simplicity. But before going over the actual chapter, it would be a good idea to review finding the domain of a function of a single variable function. So very important fact that will actually be applied to functions of multiple variables, by the way, so it should work the same. For example, let's consider a few facts. One thing to keep in mind that is that the domain of polynomial functions is a set of all real numbers. If you look at polynomials, they don't have any discontinuities, no asymptotes, gaps, or holes. And also for the domain of radical functions of odd index, right? That is the cube root function, the fifth root function, the seventh root function, etc. Though the domain of those functions is all real numbers. Now for procedures or for functions that you might want to be careful with, number one, rational functions. So rational functions, their domain is a set of all real numbers except for which the denominator is 0. Alright, so what do we do in this case? So we set the denominator equal to 0 and solve the given equation for the given variable. When we have, on the other hand, radical functions that have an even index, that is, in this case, like the square root function, the fourth root function, the sixth root function, etc., the eighth root, the 10th root. In this case, we set the radicand greater than or equal 0 and solve the inequality for that variable. To find the domain of logarithmic functions, it's going to be a similar procedure than that of the previous one with the radical functions of even index. However, in this case, we set the argument greater than 0. What is the argument? Number one, well, number one, if we recall from intermediate algebra or from college algebra, the argument is the expression inside of the parentheses of the logarithmic operator. And in this case, what's the difference between the domain, between the procedure to finding the domain and the previous one? In this case, we set it greater than or equal 0, and in this case, greater than 0 only. And the reason why is because for radicals of even index, we can evaluate them at 0. We can take the square root of 0, the fourth root of 0, the sixth root of 0, etc. As opposed to taking logarithms, we cannot take logarithms of 0 and negative numbers. So that's why we just set it greater than only. Alright, so let's find the domain. Let's review this just with some basic examples. Find the domain. So letter A, the domain, the given function rather, is a rational function. So in this case, you don't want x minus 5 to be 0, so x equals 0, right? That means that if you plug in 0 to 5 to that, you're going to get a denominator 0. So we're going to say x such that x cannot be 5. That's in the set builder notation. With interval notation, the way we express it is all real numbers except the number 5. How do we express that? Negative infinity to 5, union symbol, 5 to positive infinity. So that's how we find the domain of a rational function. Alright, for letter B, In this case, we are going to set the radicand. The radicand is the expression that lies inside of the radical. Okay, so we set this x plus 4 greater than or equal to 0 and solve the inequality. Okay, so in this case we say that x such that x greater than or equal -4, or using interval notation, it goes from -4 inclusive because of the inequality sign. Notice we have the equality as well, so that goes all the way to positive infinity. For the logarithmic function we have here, we are going to set the argument for x minus 5 greater than 0 in this case. So let's add 5 to both sides, and x should be greater than 5/4. Using set builder notation, we say that x such that x is greater than 5/4. Using interval notation, it goes from 5/4 and on to infinity. However, as opposed to the previous example, it's not going to be inclusive, it's going to be exclusive because it's only greater than. Right? Otherwise, if it were greater than or equal, like the other case, we would have used the brackets here. So this is a mini review of how to find domain of elementary functions. Let's move on to functions of several variables. Okay, so as opposed to the previous, the older functions, we are going to have the following notation. Okay, we're going to have the notation f of x, y if the function is defined into different variables. And we read it like this. We read it f of x and y, or f of x, y. It's also another way to express that that function. Okay. Now, when it comes to evaluate functions of several variables, we are not just going to be given a value of x. We are going to be given instead an order pair, like the examples that we have below, and for which they're asking us to find the domain and then evaluate them at a given point. Alright, so when it comes to finding the domain of of a function of several variables, so we need to find it individually. Okay, and in this case we are just going to use set builder notation. We are not going to use interval notation, and we are going to express it x comma y, which is all the order pairs x, y, such that, well, in this case, let's go alphabetically. So for the numerator we have only an x, but notice that the x is inside of a radical of even index, for which x cannot be negative. So that's all we do. X has to be greater than 0. And then the denominator, we have a y squared. So if this were only a polynomial, it would be all real numbers for y. However, look at the location of the variable y. The variable y is in the denominator, and the denominator cannot be 0, so y cannot be 0. Okay, so from here all we do is evaluate the function at the given point. So we go f of 9 comma -1 and plug in the numbers where they correspond. 9 for x and -1 for y. Square root of 9 over -1 squared. This is 3 over +1, which is 3. Alright, the final answer will give rise to an order triple. The order triple, 9, -1, and 3. Let's look at another example. Alright, Looking at this example, g of u and v, in this case it's not xy but u and v, but it's still the same. We can treat them the same usual way. Alright, so in this case, let's start by finding the domain, which in this case is the order pairs u comma v, such that, okay, this is not supposed to be a t, it's just a bar, such that, well, let's look at every single variable in alphabetic order. So what about u? So in this case, notice how u is in the exponent of the exponential function, and it's not inside of a radical or the argument of a logarithmic function or inside of a radical. However, if we look at the second term, I would be in trouble when it comes to plugging in values for u. Alright, so in this case, because of this logarithmic part, I wouldn't be able to just plug in any number, only u greater than 0, because the logarithmic function cannot eat the number 0 or negative numbers. Now what about v? So in this case, v can take any value. So v belongs to the set of all real numbers. Alright, so that's how we would evaluate this. We express this. This e means belongs to, and this fancy stylish r means real numbers. So let's evaluate the function at the given point. G evaluated at u equals 1, v equals to 2. So e to the u, which is 1 times 2, minus ln of u, which is 1. Okay, so e to the 1 times 2, that's going to be e to the second power, but ln of 1 is 0, which is simply going to be e squared. So the order not pair, but rather the order triple will be 1, 2, and e cubed, squared rather. Okay. Let's look at the third example. So for the third example, we have a combination of pretty much everything here. So let's see, in this case we have x's and y's back again. Alright, the domain will be x comma y's, the orders x, y, such that, well, what about x? X, notice it is part of a logarithmic function, so I need to restrict that to have x greater than 0 only. And the y, notice how it is inside of a radical function. So in this case, y can take any value that is 0 or positive values. Okay, so from here we evaluate f at e comma 4, which in this case we're going to have ln of v e raised to the square root of 4, where the square root of 4 is going to become a 2, and ln of v will be 1. So in this case, the order triple that we are going to have will be e 4 1 over e squared. Okay. Now let's move on to the next topic. Now, how do we graph functions of two variables? So unfortunately, graphing functions of two variables, it's not an easy spin. So we are just going to limit to look at very basic, like I'm gonna graph a plane on the next page, but here let me show you how do we graph a point, at least in the 3D space. So for example, we want to graph the point 2, 3, 4 as described in the picture here. So in this case, this is the x-axis, the y-axis, and the z-axis. So we move 2 units in the x direction, and then 3 units in the y direction, and 4 units up in the z direction. However, we need to be very careful with the perspective. So and it's not easy to draw a solid using too many points. The same way it was easy to draw like parabolas or lines or trigonometric functions in the other types of functions, in the 2D functions. So how do we graph a plane? So what we have here is a linear equation in 3 variables, right? So let's write that down. Which is this. So if we didn't have this term with the c, we would have a line, the equation of a line in 2D. However, in this case, this is going to be a plane. Alright, so how are we going to graph this plane? Well, so we're given an equation. Sketch the graph of the plane described by 2x plus 3y plus 4z equals to 12. Alright, so let's see. Number 1, we are going to do this by finding the intercepts. So we are going to find, number 1, the x-intercept. To do that, I'm going to cover y and z. In other words, I'm going to let the other variables y and z equal to 0 and find this x-intercept. So 2x plus 3 times y plus 4 times y, which is going to be 0 in all cases. So that's going to be 0 and 0. And in this case, well, this is are going to get zeroed out. 2x equals 12 and x equals to 6. So that means the x-intercept, well, in this case, there's only one. We need to use the plural version of it. So it's going to be 6, 0, 0. Let us now find the y-intercept. We're going to take a very similar approach, but in this case, since I want the y-intercept, I'm going to set x and z equals to 0. Okay, I'm going to set both equal to 0. So 2 times 0 plus 3y plus 4 times 0 equals 12. That's going to be 0 and 0, 3y equals 12. So y is going to be 4. That means that the y-intercept will be 0, 4, 0. Let's find the z-intercept. Find the z-intercept. So in this case, to get the z-intercept, we are going to set x and y equals to 0. So 2 times 0 plus 3 times 0 plus 4 z equals to 12. Okay, get those zeros, we get 4 z equals to 12. So z equals to 3, which means that z-intercept is 0, 0, 3. Alright, how are we going to plot this plane? Well, first of all, let's make 3D plane, well, a 3D graph, not a 3D plane. Well, otherwise that wouldn't be plane. So I'm gonna have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Okay. So we're gonna graph the x-intercept. I'm gonna go 1, 2, 3, 4, 5, 6. That's 1 here, and then 1, 2, 3, 4 in the y direction and 3 in the z direction. And we are going to draw the triangle here that corresponds to the plane intersecting these 3 points. And if you want to give some effect here, by all means. Okay. Alright, and that's our plane. That's how we will graph our plane. So this one is fairly easy to draw. It doesn't require, you know, to be more perfect when it comes to curvy or like other parabolas. I mean, like there's a bunch of other solids like paraboloids, ellipsoids, and many other surfaces that we are not going to bother and graph. All right. So let's move on to the next topic. So in this case, well, we cannot just have functions of 2 variables. We can have functions of more variables, like 3 variables, 4 variables, infinite, many variables as you want. All right. So for example, these are functions of 3 variable functions and 1 4 variable function. So in this case, if we observe this one, all right, that's V of L WH. That describes the volume of a rectangular box. Which we are going to be using kind of soon from now. We're going to use that. And then for the next one, you might have seen this PERT formula, which is also a 3 variable function. It's for compound in continuous compound interest. Okay. And then we have this f of w, x, y, z. Well, we're adding these 4 quantities and dividing by 4. Well, this is the average, or if you want to see this from the statistics point of view, the mean of 4 quantities. Alright, let's do an example in which we are going to find the domain of a function of 3 variables. So in this case, it's going to work the same. Okay, so in this case, I'm going to add one more letter, x, comma, y, comma, z. So all the other triples such that, okay, what about x? Okay, the only x I see is here inside of the radical. Alright, so in this case, x cannot be negative, only greater than or equal to 0. Let's look at the y. Well, the y is right there as well. So in this case, y cannot be 0. And finally, the variable z. Notice about the position of z. Z cannot be 0, but also because it cannot be it's inside of a logarithmic function, it cannot take negative values, so z has to be strictly greater than 0. Alright, so let's just evaluate f of 4, -1, 1. Okay, 4, -1, 1, and write them where they correspond. So this is going to be the square root of x, which is 4, divided by y, which is -1, plus ln of 1 over 1, which in this case this will be square root of 4, which is 2 over -1. That's going to be -1 again, plus ln of 1. But what's ln of 1? ln of 1 is 0, so this is going to be -2 plus 0, which will be -2. So this will give rise to the order quadruple for -1, 1, -2. Applications. Alright, so these functions have a lot of fun applications to finance and also science and geometry as well. So let's look at this word problem. So a company manufactures 3-speed and 10-speed bicycles. Alright, let's highlight all these pieces of information. So 3-speed and 10-speed. There's this company manufacturing these two types of bicycles. So it costs $100 to make each 3-speed. Okay, let's highlight with the corresponding color. And it costs $150 to make each 10-speed bicycle. And there's of course a bunch of fixed costs, right? Because I mean, there's a lot of expenses when someone has a manufacturer, right? For example, this money might be used as fixed costs, maybe to pay the employees, to pay insurance of the place, to pay the bills of the factory. So those are the fixed costs. So it's not just going to be the cost of building, of manufacturing the bicycles. So in this case, I'm going to highlight with another color. Let me find a good color. Let me use blue. Fixed cost $2,500. Find the cost function, the total cost function, and use it to find the cost of producing 15 3-speed bicycles and 20 10-speed bicycles. Alright, so we are going to set the following function. So cost, which will be 3-speed plus 10-speed plus fixed costs. Alright, fixed cost. So in this case, they're telling us that it costs $100 to make each. So that means each X, let's call that X. By the way, the 3 speeds are going to be labeled X. And it costs $100 to build, to manufacture one, and $150 to manufacture Y 10-speed. Plus the fixed cost, which is $2,500. So in this case, we are defining a cost function that depends on X and Y. So that's the function we are going to use to find the total cost of producing 15 3-speeds and 20 10-speeds. So evaluate 15, 20. Alright, so in this case, let's plug in the numbers only 15 and 20. And let's just use a graphing calculator to simplify this operation. So let me time 100 times 15 plus 150 times 20 plus 2500, and we get 7,000. So 7,000 is the cost to manufacture all these bicycles. Okay, final answer here. Let's move on to the next page. Let's see what's in there. A very typical problem in applied biology is using this formula right here, which is useful to find the surface area of a person that weighs W pounds and has a height h in feet. So it's an approximation. It's not a perfect, it's not the exact answer, but it's a good approximation. So we're going to use this formula to find the amount, basically the amount of skin in terms of area, a person who weighs 150 pounds and is 5 feet tall. So A evaluated at W, which is 150, comma 5, equals 0.55, W to the 0.425, H to the 0.725. So let's plug in the numbers. 150 here and 5. Keep in mind this is a multiplication. Again, let's just use a calculator for this. So I'm going to 0.55 times 150 raised to the 0.0245, or wait a minute, 425, 0.425 times 5 raised to the 0.725. So we get 14.85. And typically we round to one more decimal than the data that is given. So in this case we were given all integers, so we round to, in this case, one decimal place, which will be in this case 14.9 feet squared. Those are going to be the units. Simple calculation. You're given the formula, plug in the numbers, that's all you do. Alright? So this is the end of this section. I'll see you on the next video.